Hey everyone, in the last video we talked about simple data encoding formats and also their limitations. In this video we'll talk about two binary encoding protocols which are Thrift and protocol buffers. Protocol buffers, it was originally developed at Google and Thrift was originally developed at Facebook, and both of them are open source now. So let's first understand Thrift encoding with an example. Now let's say we have this example data containing a username, a favorite number, and an array of interest. Now let's see how we can serialize this data with different encoding schemes. So first let's talk about Thrift. So both Thrift and protocol buffers, they require a schema for any data that is encoded. To encode the data that we saw in the previous slide with Thrift, you would have to describe the schema in Thrift ideal, which is interface definition language. So this is the Thrift ideal. In this case, you define a struct, and then you have 1, 2, 3 as tag numbers. So this tag number is it's tied to every field that you have in this schema. Also, the field favorite number and interest, they are optional fields. So favorite number is an integer, int 64, username is a string, and interest is an array of strings. Also, both Thrift and protocol buffers, they each come with a code generation tool that takes a schema definition like the one shown here, and it produces classes that implement this schema in various programming languages. So then your application code can call this generated code to encode or decode the records of the schema. So this is what the data encoded with this schema looks like. Now Thrift has two different binary encoding formats. One of them is BinaryProtocol and the other is CompactProtocol. So this slide is about BinaryProtocol. So as you can see, Thrift encodes this whole data in just 59 bytes. Whereas if you use JSON to encode the same data with white space removed in textual form, then it will take around 81 bytes. So great savings of space. Now let's break down each of these fields, username, number, and interest, to see what these bytes actually represent. As you can see, each field has a type annotation to indicate whether it is a string, integer, list, etc. And also when required, a length indication which shows the length of the string or number of items in the list. Now the strings that appear in this data, for example Martin, Daydream, Hacking, they are all encoded as ASCII characters. Now another thing to note here is that there are no field names. For example, the field name, username, favorite number, or interest, they're not encoded in this version. So instead, this encoded data, it contains field tags, which are numbers 1, 2, and 3, which we saw in the struct. Now these are the numbers that appear in the schema definition. So field tags, they are like aliases for fields. They are a compact way of saying that what field we are talking about without us actually having to spell out that field name. So for username, its type is string, which has a value of 11 in Thrift, and 11 is written as 0b in hex. Then 2 bytes are allocated for the field tag. So username has a field tag of 1, as we saw in the schema. Then 4 bytes are allocated for the length field, which is 6 here. And then the word Martin is encoded. So M has an ASCII value of 77, which is 4d in hex. Then A has an ASCII value of 97, which is represented as 61 in hex, and so on. So also for this number 1337, these two fields are the same. Type 10 is the type of the int 64 and the field tag is 2 here. So the number 1337, this is also represented in hex. So 8 bytes are assigned for an int field here. So any 64-bit integer, it will be able to fit in these bytes. Now encoding the interest array, it also follows the same pattern. There are some bytes here to denote the number of items in the array, which is 2 here. And then the length and the string value is encoded the same way as the other two fields. So the Thrift compact, so the one that we talked about was Thrift binary protocol. Now the Thrift compact protocol, this encoding is semantically equivalent to the binary protocol, but as you can see, it packs the same information in just 34 bytes. So that's a great reduction in space complexity. And let's see the breakdown to understand how it packs all these values so efficiently. Now the compact protocol, it's able to pack efficiently because it packs the field type and tag number into just a single byte. So while the binary protocol it used a total of 3 bytes to encode both of these things. So for username, 4 bytes are allocated for the field tag, and then 4 bytes are allocated for the field type, which is string. So all this info just fits in 1 byte, which is 18 in hex. Also for integers, it uses a variable length integers. So rather than using full 8 bytes for the number 1337, it just encodes the number in just 2 bytes. So this is how encoding of number works in case of Thrift compact protocol. I'm not going to go into the details of this. You can this example or this algo is taken from the Thrift GitHub doc, so feel free to check it out. It just first converts the number into a zigzag int using this code, and then there are some bunch of steps like left padding to make it into a group of 7, and then adding MSB prefixes and then converting it into little endian format, and then finally getting the hex. So for encoding the interest array, again it packs the array length and the item type in just 1 byte. So also some space saving here, and the rest of the things, they are similar to other fields. For example, the length and the string content, they are similar to the other string that we saw. So great win overall in terms of space needed for encoding in case of compact protocol. Now finally, protocol buffers, they have only one binary encoding format. It encodes the same data in this way. So it does the bit packing slightly differently, but it's otherwise very similar to Thrift's compact protocol. So protobufs, they fit the same record in 33 bytes. Now they also combine the tag, the field tag and the type in just 1 byte. So these two go into just 1 byte, and then there is a length field, and then again the string contents. Now in case of ints, for encoding the ints, the number 1337, they have a slightly different logic from Thrift, but they are able to fit this number 1337 again in 2 bytes. So I'm assuming they also use some kind of zigzag encoding, and they use a variable size for encoding the integers. And for encoding the list, it encodes each element of the list with the same tag number combined with its type, which is string here. So in case of these two elements of the string, it uses the same field tag as 3 and then the type as string. So length of the first element of this array is 11, and in this case it's 7, and then the strings are encoded. So protobufs are able to encode this data in 33 bytes, which is almost the same as Thrift in terms of space complexity. So we discussed previously that schemas, they inevitably need to change over time, and this process is called schema evolution. Now let's see how do Thrift and protocol buffers, they handle schema changes while also keeping the forward and backward compatibility. So as you can see from the examples, an encoded record, it's just the concatenation of its encoded fields, and each field is identified by its tag numbers, which are the numbers 1, 2 and 3 in the sample schemas, and also a data type. So from this we can see that the field tags, they are very critical to the meaning of the encoded data. So you can change the name of the field in the schema, because the encoded data, it never refers to the field names, but you cannot change a field tag, since that would make all the existing encoded data invalid. So if you are adding new fields to the schema, to keep it backward compatible, make sure that you are not adding any required fields, because the new code, it will try to read the data which the old version of the code won't write. So always add optional fields to keep it backward compatible. Also, if you are using optional fields, you have to give each field a new tag number. So in that case, if old code which doesn't know about the new tag numbers which you just added, when it tries to read the data written by the new code, it can simply ignore that field. And it's the same when you are removing a field from the schema. So that means you can only remove a field that is optional. A required field, it can never be removed. So also you can never use the same tag number again. This is because you may still have data written elsewhere that includes the old tag number, and that field must be ignored by the new code. So let's say if we change the data type of a field. Now that may be possible, but there is a risk that values will lose precision or they will get truncated. So for example, let's say you change a 32-bit integer into a 64-bit integer. Now new code can easily read data written by the old code because the parser will be able to fill in any missing bits with zeros. However, if old code, it reads the data written by the new code. Now the old code is still using the 32-bit variable to hold the value. So if the 64-bit value, it won't fit into the 32 bits, it will just be truncated. So that's it for this video. Now in the next video, we'll look at Avro encoding and how it compares with